Alright, let's see here. I gotta adjust this. This isn't my usual phone. On the backup phone. So a little bit more on angled forces for you to kind of think about and practice with. Again, the whole point here is, dealing with forces when they're not just simply horizontal. Right? Classic thing here. We got a force. Let's say it pulls at an angle of, we love 30 degrees, right? That's a nice angle. And we pull it at a constant velocity, right? So this is what that first problem really is all about. The whole point here of this is when you have this angled force, let's just make it 100 newtons. When you have this angled force, it's pulling up and to the right. It has, again, we've been talking about this in class, but it has a y component and an x component. Now, I make them dashed vectors because they're not extra forces. You got to be careful there. They're a representation of how much this force is pulling up and how much is pulling to the right. Now, in class here, I took let me grab a protractor quick. Let me just pause this and grab a protractor and show you. Alright, I took a protractor in my class yesterday and showed them this, but the reason we can do this, right, is because vectors, the length of them is directly proportional to how strong they are. Alright? So if I make a real triangle out of this, right, like let's make a real scale force time. Let's take that force and break it into components in a real triangle, alright? 100 newtons in length. So I'm gonna say, okay, 100 newtons is, I'm gonna do a scale drawing of this vector. So 10 newtons per centimeter. 1 centimeter. That's kind of like our key. 10 newtons per 1 centimeter. So first I have to make the angle, right? So good old protractor. There's the center point, 30 degrees is right there, right there. All right. So a horizontal is, I'm just going to do a dashed line here for horizontal. That's kind of terrible, but oh well. Here's our line. You got to be careful when you do this that the tip of it is at the end of it, and this is 30 degrees. Actually, I have to make it the right length, 10 centimeters. There it is. Almost. Alright, so mess that up a little bit, but that's okay. 10 centimeters at an angle of 30 degrees. So what I could do is I could draw the actual triangle here now. And because the length of these lines are proportional to the strength of the force, if I go ahead and measure the height of this triangle, which appears to be, about 5 centimeters. All right. And about 8.8 centimeters. All right, so that would be correspond to 50 newtons and 88 newtons. All right, so I can actually, represents the force, the length of this side of the triangle. The length of this side of the triangle represents how much the force is pulling up. That's Fy. This represents how long it's pulling to the right. That's Fx. This is 100 newtons. I drew it to scale and I just literally measured the height and the base. So that means Fy, the y component. Now keep in mind, technically the x and y component are here and here, Fy and Fx. But since it's a rectangle, the height of the triangle has to be the same length as that. That's how you can do it geometrically. Now, we wouldn't want to do that every time, right? Draw scale drawing. That's no fun. Well, it's kind of fun, but it would be a pain in the butt on the test, right? So what we do is we use trig, right? Rather than measure, we say, okay, I know that's 30 degrees, that's 100. I need to find what is usually called the opposite and adjacent side, right? So I would say cos of 30 equals adjacent over hypotenuse. The adjacent side is our fx. The hypotenuse is our force, which is 100 newtons. So I solve this for fx now, so I multiply both sides by 100. All right, then I take my calculator. I always make sure it's in degree mode when I'm in physics class, so it's 100 times the cos of 30. That equals 87. This is equal to 87 newtons. That equals the x component of the force. All right, the y component of the force, I would say, I'll do it up in this area here. I would say sine of 30 equals opposite, which is the y component of the force, over hypotenuse, which is 100. All right, multiply both sides by 100. I know the sine of 30 is 1/2, so it's 100 times 1/2, or 50 newtons, equals Fy. And our measurements came out very close to that. All right. So, what are we doing with this? Well, we're going to say, okay, what force is needed? So here's an example for you. This is similar to one of the problems we're going to be looking at here in class. The worksheet problem number 3, I think, or 4, problem 4, where I give you a force, and I say, okay, that's a 50 Newton force at a 25 degree angle. What forces would have to balance that out, right? All right, so think about problem 1 on worksheet 4, where the total up forces have to cancel the total down forces, and the total forces pulling to the right must cancel the total forces pulling to the left. So our up force here is actually, the y component of the 50 Newton force. The component, the force pulling to the right, is the x component of the 50 Newton force. All right. So if I want to figure out what this force pulling to the left is, well, I got to figure out then what the component of this angled force is, the x component. If I want to figure out the force pulling down, I have to figure out the y component of this angled force, because again, this y force has to balance this force. This x force has to balance this force. The angled force, you got to look at it either way. These aren't 3 forces. There's really only one force balancing out these 2 forces. I'll call these F1 and F2. And I'll call this F. All right? This is the only real force. All right? This force is balancing out both of these. But its x component is balancing this out. Its y component is balancing this out. All right, so let's figure out the x and y component. We're typically given the angle here. I like to draw the triangle each time anyways, just kind of off to the side. 25 and 50. And I don't even put units on the force, right? Because I'm looking for this side, Fy, and this side, Fx. And it's just fairly repetitive, right? Cosine of 25 degrees equals Fx over 50. All right, so Fx equals 50 times the cos of 25 degrees. 50 times cos 25 is 45. So the x component of this force is 45 newtons. So that means when I put it on this diagram, it's actually positive 45 newtons. So that means F1 must be negative 45 newtons. All right, so it balances left to right. Then over here, I say Fy equals 50 times the sine of 25. Oh, look, I didn't write it out. All right, I didn't write out the sine 25 equals Fy over 50. All right, it always ends up in this format. Sometimes you have to put cosine with y and sine with x though. For instance, if I gave you this angle, right, the opposite side is x. So you use sine of this angle equals x over 50. Fy in this case would be the adjacent side. So it depends on the angle, which of the angles you're given. They're always going to be right triangles though. So that's the nice thing. All right, so 50 now. 50 times the sine of 25 is 21. So Fy is 21 newtons. So that means this is 21 newtons. Therefore, F2 must be negative 21 newtons. All right? Now, it's very important that the x and y components you draw as dashed line vectors and not solid lines, okay? If you make them solid, you're saying that that's an extra force, and it's not, all right? Pause this for a second, get another sheet of paper. All right, now let's look at an example where we go the other way, okay? Let's say we have a box, right? And it's hanging from a garage ceiling or something. All right, so there's a ceiling, there's the box, but it's in kind of a corner. And this is one of the next problems you're gonna do, problem 5, all right? It's got 2 ropes attached to it. It's got one hanging it this way and one connected. That's not a great drawing. This way, I'll make this one thicker to make it look a little better. All right? It's got 2 ropes hanging it. Maybe it's like, I don't know. Maybe it's something you're gonna swing, or I don't know. Could be anything. I have a story about this, but I'll save it for class. So this is some sort of box. Let's give it a mass. Let's say it's a 10 kilogram box. All right, it's got these 2 ropes. Well, I want to figure out how strong these ropes have to be. All right, let's say when we measure the angle, right, to the ceiling, we see it's about 65 degrees, the angle at the ceiling. All right. So we've got 1 rope here holding it. It's going to be pulling. Remember, when we draw a force diagram, we're drawing the forces acting on the object, right? This is the whole point of going through this slowly. The box here is the object. That represents the box. So what forces are acting on the box? Well, we got this left rope pulling it this way, right? That's F1. We've got this rope pulling it up that way to keep it from falling. I'm going to call that F2. And there's one more force that we can't see. It's the force of the earth pulling it down, which we call Fg. All right? So this is cool. This looks like our last problem, the force diagram. So I'm going to draw my coordinate system here. All right. There's our coordinate system. This is the positive y. This is the positive x. Now, this angle, 65, right? How does that translate to this drawing? A lot of people will say this is 65, but it's not. It's actually, I did a poor job with this force vector. I should have made it more up like that. Because this angle is actually the same as this angle, right? So that means that this is 65 degrees right here. So now, what do we do with this? How do we figure this out? How do we figure out what the tension in these 2 ropes are? Where do I start? Well, I have no idea. What else was I given? Well, I know the mass of it. I know the mass is 10 kilograms of that object. So that means Fg must be negative 100 newtons. All right? So the force of gravity is negative 100 newtons because it's the mass, again, that is mg, right? And the sine, so the mass is 10, g is about 10, so it's 100. newtons is the weight. Negative is because it's going down. So it's just like problem 1, we have a down force. The up force must also be 100 newtons. So that means, all right, F2, we break it into its x and y components. So I'm going to draw them dashed to try to make them look a little bit bigger than the axis lines. And I do not draw them as solid lines, all right? So F2y and F2x, right? Those dashes are just to show that they line up there. So this would be F2y. Now if I had a pencil, I would write that nice and light, and that's F2x. Well, here's what we do. This is Newton's second law. You start by drawing a force diagram, right? Then what you do, no matter what, is you break. So step 1, draw force diagram. Step 2 is use trig to write equations for angled vector components. Alright, hard to read there, sorry. Use trig to write equations for angular vector components. These are steps to setting up these problems. So, the trig I'm going to do over here. Okay, so the trig is F2y has to equal F2, and it's the opposite side we're trying to find here, times the sine of 65 degrees. F2x must be F2 times the cos of 65 degrees because it's the adjacent side we're looking for. So look back at the previous example to see how I use so and ka to do that. All right. Well, I know that F2, I don't know F2, but I do know F2y must be equal to positive 100. So how do I use that information? All right. So I set up force equations for each direction, okay? I do one for the x direction. And what I do here is I compare the up and down forces. Now there's two ways to think about this. You can think about the total up forces having to cancel the total down forces. All right? Or you could think about adding up the forces must be equal to 0 because you know what? F total, which we call F net, along the x direction must add up to 0 newtons. In the y direction, F net y must also add up to 0 newtons. That means they must cancel, right? The total force up and down must cancel. So let's start with the y direction because we have some information there. All right, so in the y direction, F net y is the sum of the two forces. So it's F2y plus Fg must equal 0 newtons. We're really just saying what we're really just making an equation for what we already know is true, right? So F2y plus, and what's Fg? It's negative 100 newtons must add up to 0, right? So really all we're saying is that F2y must equal positive 100 newtons, which you guys know that already from what we've done, right? You can look at this and say, okay, the up force must cancel the down force, right? So if I have 100 newtons of weight going down, the y component of F2 must be positive 100. You could have done without this, but I want you to see this because as we get more complex, you're absolutely going to have to solve these this way. F net x now. Now, that's cool, FTY. So when I think about my triangle here, right? So if I think about my triangle, then I'm trying to figure out this side is, now we know that side has to be 100, right? Or sorry, this side has to be 100. Yeah, no, sorry. Jeez. The vertical side has to be 100, and I know that this is 65 degrees. Once you know that, once you know two things about a triangle, you can figure everything else out. Right? right? Once you know two things, you figure everything else out. So let's talk about the, let's go ahead and find this hypotenuse then, right? So it's like, there's kind of like three things going on here. We got the force diagram, all right? 3 is to set up Newton's second law equations. Set up Newton's second law. That's step 2. That's what this was. Step 4, so we've got 1, 2, 3, and then, you know, step 4 kind of happens at the same time. You use the trig and the geometry to solve for answers. So let's hold off on the hypotenuse. Let's figure out what's going on in the x direction. So in the x direction, what we have is F2's x component plus F1 must equal 0 newtons. All right? So here's the trick here. F1 has got to be equal in magnitude to F2x, but it's going to be negative, right? These two have to be the same size, but F1 is going to be negative. So we got to figure out what F2x is, and once we know that, we'll know what F1 is. Since we know F2y, we can figure out F1 and F2. And again, we're trying to figure out the amount of force in these two ropes here. All right? So, being applied by these two ropes. So now we have to, you know, we have to use trig, step 4, use trig to figure out unknown forces. All right, use trig to figure out unknown forces. So, I know the opposite in F1. So sine of 65 degrees equals 100 over F1. So therefore, F1 must equal 100 divided by the sine of 65. We cross multiply here, right? So 100 divided by the sine of 65 is 110. 110 newtons. So I know now, right, that the hypotenuse of this triangle is 110 newtons. So that's F2. I'm sorry. F2, 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 F2. The hypotenuse is F2. Sorry, my bad. So I know now F2 equals 110 newtons. All right, so there's one of my answers. Now, if I figure out the adjacent side here, so I'm going to have to bring in a little extra paper here. If I want to figure out the adjacent side, I would say cos of 65 degrees equals F, and that's F1, you fool, equals F1 adjacent over hypotenuse, 110 newtons. So F1 equals 110 times the cos of 65 degrees. You could have used a tangent here as well, but you know, that's all right. 110 times the cos of 65 equals 46 newtons. So F1 has to be 46.5, I'll say 47 newtons. So 47 newtons. So if F1 is 47 newtons, so let me go back up here now. All right, if we know F1 is 47 newtons, F2x plus 47 must equal 0. Therefore, F2x, which is simply, oops, man, Harmon, you're really messing up. F2x is 47 newtons, we know. That should have been F2x down there. Then I know if I bring that over there, it should be F1. This should be F1. Bring the 47 over here. F1 must be negative 47 newtons. Now, I know this seems very long, and I apologize for that. Really, we could have done this quite a bit quicker just by saying, all right, I know this is 100 on the triangle. Figure out the other two sides and make the answer. All right, but this procedure here, I want you to see this and do this, you know, sometimes, because as we get more complex, you'll need that framework, okay? So see what you can do with problems 5 and 6 there. Should be, you know, at least give you an idea of where you're going with it. And we're going to go over this stuff much more in class and see how it goes.